In late 2018 and early 2019, the aviation world was stunned by two fatal crashes involving Boeing's brand new 737 MAX aircraft. First, Lion Air Flight 610, then just months later, Ethiopian Airlines Flight 302. In total, 346 lives were tragically lost, and a pristine safety record was shattered. These weren't isolated incidents of mechanical failure or pilot error, they pointed to a deeper, systemic issue within the design and certification of what was meant to be Boeing's next-generation workhorse. What truly went wrong, and why did a modern airliner fail so spectacularly? The Boeing 737 MAX was introduced in 2017 as the fourth generation of the venerable 737, an aircraft family that has been the backbone of air travel for decades. It promised greater fuel efficiency and range, primarily through new, larger CFM LEAP 1B engines. But these larger engines presented a problem: they had to be mounted further forward and higher on the wing, changing the aircraft's aerodynamic characteristics. Boeing's engineers needed a solution to make the MAX fly like its predecessors without extensive, costly redesign. The pressure on Boeing was immense. Airbus had launched its A320neo, a re-engined version of its popular A320, years earlier and was quickly gaining market share with superior fuel efficiency. Boeing felt compelled to respond swiftly, opting for an update to the 737 rather than an entirely new aircraft design. This decision was driven by the desire for a faster time to market and lower development costs, estimated to be a fraction of what a truly new plane would require. This strategic choice would have profound consequences. To counteract the aerodynamic changes caused by the new engines, Boeing introduced the Maneuvering Characteristics Augmentation System, or MCAS. This software system was designed to automatically push the aircraft's nose down under specific flight conditions, mimicking the flight characteristics of older 737 models. Crucially, MCAS operated in the background, initially with little to no mention in pilot manuals or training materials. It was meant to be invisible to pilots, a design choice that would prove catastrophic. The fundamental flaw in MCAS wasn't its existence, but its implementation. Boeing designed the system to rely on input from only one of the aircraft's two angle of attack, or AOA, sensors. If this single sensor malfunctioned, it could feed erroneous data to MCAS, causing the system to repeatedly push the nose down, even when the aircraft was not in a stall. This single point of failure was compounded by the fact that MCAS was designed to exert significant authority over the aircraft's trim system, making it incredibly difficult for pilots to counteract. On October 29, 2018, Lion Air Flight 610, a brand new 737 MAX, crashed into the Java Sea shortly after takeoff from Jakarta, Indonesia, killing all 189 people on board. Initial reports revealed erratic flight path data and a struggle between the pilots and an automated system. Investigators soon discovered that a faulty angle of attack sensor was feeding incorrect information to the MCAS, which repeatedly commanded the aircraft's nose down. The crew fought for control, but without proper understanding of MCAS, they were tragically outmatched. Following the Lion Air crash, investigations began, and Boeing issued an operations manual bulletin, instructing pilots on how to counteract uncommanded nose-down trim. However, this bulletin did not explicitly name MCAS or fully explain its aggressive behavior. Regulators, including the FAA, largely deferred to Boeing's assessments. Crucial opportunities to ground the fleet or issue clearer, more urgent warnings were missed. The incident was largely attributed to a chain of events, including maintenance issues and pilot responses, rather than a fundamental design flaw. Just 5 months later, on March 10, 2019, history tragically repeated itself. Ethiopian Airlines Flight 302, also a 737 MAX, crashed 6 minutes after takeoff from Addis Ababa, killing all 157 people on board. The flight data recorder revealed a chillingly similar pattern to Lion Air 610, an erroneous AOA sensor input, followed by repeated, uncommanded nose-down commands from MCAS. Despite following the emergency procedures outlined after the first crash, the pilots were unable to regain control. This second crash removed all doubt: the problem was inherent to the aircraft. The similarities between the two crashes were undeniable, and the global response was swift and unprecedented. Within days of the Ethiopian Airlines disaster, countries around the world, one by one, began grounding the entire Boeing 737 MAX fleet. From China and Europe to Canada and eventually the United States, airspaces were closed to the MAX. This wasn't just a corporate crisis, it was a crisis of confidence in one of the world's most trusted aerospace manufacturers and its regulatory overseer. Over 380 aircraft were immediately put out of service globally. With the global grounding in full effect, the focus intensified on MCAS. Investigations by the NTSB, the EASA, and other international bodies converged on the system's design. It was confirmed that MCAS was indeed the common thread, repeatedly forcing the nose down based on faulty sensor data, leading to an unrecoverable dive. The aggressive nature of MCAS, combined with its lack of redundancy and pilots' lack of awareness, created a perfect storm. This revelation pointed to fundamental flaws not just in software, but in Boeing's design process itself. Many analysts attribute these failures to a significant cultural shift within Boeing. Historically, Boeing was an engineer-led company, prioritizing safety and innovation above all else. However, following its merger with McDonnell Douglas in 1997 and increasing pressure from Wall Street, the culture reportedly shifted towards cost-cutting, maximizing shareholder value, and rushing products to market. This new emphasis on finance over engineering excellence is seen by many as a critical underlying factor that allowed the MCAS design flaws to persist. Equally critical was the failure of the Federal Aviation Administration, or FAA, which is responsible for certifying aircraft safety. For decades, the FAA had delegated significant portions of the certification process to Boeing itself, relying on the manufacturer's own employees to conduct safety assessments and testing. This designee program, meant to streamline the process, fostered an overly trusting relationship that ultimately compromised independent oversight. Key design changes, including the full scope and authority of MCAS, were not adequately scrutinized by the agency. The scrutiny revealed that the certification process for the 737 MAX was deeply flawed. Firstly, Boeing deliberately downplayed the role and authority of MCAS to avoid triggering requirements for extensive pilot retraining, which would have been costly and delayed market entry. Secondly, the FAA's own engineers and safety experts had concerns but were reportedly pressured by management to speed up the process. Thirdly, inadequate documentation meant key details about MCAS were not fully understood by regulators or pilots. This confluence of factors led to a compromised safety review. A critical aspect of the crisis was the complete absence of MCAS in initial pilot training for the 737 MAX. Boeing's rationale was that MCAS was designed to be transparent, acting in the background, thus not requiring specific pilot instruction. This meant that when MCAS malfunctioned, pilots encountered a system behavior they had never been trained for and likely couldn't identify. The reliance on simple iPad-based training, rather than full-motion flight simulators, further exacerbated this knowledge gap, leaving crews unprepared for the unexpected. Following the grounding, Boeing embarked on a massive effort to fix the 737 MAX. The primary solution involved a significant software update to MCAS. This update now requires MCAS to receive input from both AOA sensors, cross-referencing their data, and it will only activate once per AOA disagreement. Furthermore, its authority has been reduced, and pilots are now fully informed and trained on the system. This comprehensive overhaul was critical, but the process of recertification by various global regulators took over 20 months, highlighting the damage done to trust. The financial repercussions for Boeing were staggering. The 737 MAX grounding led to billions of dollars in losses, affecting production, deliveries, and compensation to airlines. Estimates placed the total cost to Boeing upwards of $20 billion, including production halts, deferred orders, and direct payments to families of the victims. Its reputation, built over a century, took a severe hit, reflected in its stock price and market standing. The crisis became a stark reminder that prioritizing short-term financial gains over safety can lead to unimaginable long-term costs. The return of the 737 MAX to service has been a slow and cautious process, with regulators demanding rigorous oversight. Boeing faces the monumental task of rebuilding trust with airlines, pilots, and the flying public. This will require not just technical fixes, but a fundamental shift back to its engineering-first culture and a renewed commitment to transparency. As aviation expert John Nance stated, safety is not a gadget, it is a process. The MAX crisis underscored that complex systems demand vigilance, redundancy, and an unwavering focus on human factors. The Boeing 737 MAX crashes serve as a sobering lesson for the entire aerospace industry. They highlight the perils of prioritizing speed and cost over safety, the critical need for independent regulatory oversight, and the imperative of comprehensive pilot training. Moving forward, both manufacturers and regulators must embrace a culture of transparency and rigorous scrutiny. The lives lost demand that these lessons are not just learned, but permanently embedded into every design, every certification, and every flight, ensuring that such a tragedy never happens again in the pursuit of progress.